Good afternoon, everybody. My name's Axel Miller. I'm the Deputy Director at SAMS UHI, where this afternoon's speaker, Professor John Howe, is based. A very warm welcome to this inaugural lecture. It's a very fitting event for this United Nations World Oceans Day, so the timing is perfect.
Thank you very much, Todd, and thank you very much, Axel. It's a pleasure to be with you here. I'll just start my video. I'm over here in Strangford Lough in Ireland, and it's an absolute delight. I'll just start sharing with you now and tell you a little bit about what we're doing over here. Axel, you're on screen. Can you hear me and see my first slide, please? Just a quick check. Thank you. Thank you very much. So that was a really nice introduction. I hope this talk can live up to that. This is I hope will be an interesting talk for everybody. Just talking about seabed mapping. And as Axel's already mentioned, of course, happy World Oceans Day. Today is World Oceans Day. And I would like to tell you about what oceans have given to me and about how my love, my passion for the sea and mapping the seabed. I've called this Adventures in Marine Geology, and I suppose today has certainly been an adventure. So we came over on the ferry. We've just arrived with our autonomous underwater vehicle Freya, and we're here in Strangford Lough in Northern Ireland, and we're right by the harbour. And it's a lovely, lovely place. It's absolutely beautiful. You might be able to hear some noisy terns. We've got some terns outside on an island, which I think is beautiful, adds to the ambience. So thank you very much. So we're here to do some mapping. We're going to be mapping the seabed of Strangford Lough. We're going to be looking at some of these priority marine features, some of these unusual habitats, in particular things like coralline algae or merle. And the guy downstairs, as we were parking the van, has just come out and said there are orcas, there are killer whales kicking around. So I'm not sure if he's just teasing me, but we'll hopefully see something interesting. Okay, so before we get stuck in, let's remind ourselves about World Ocean Day. So this idea is, as Axel's already said, United Nations World Ocean Day is to bring people together and to celebrate and help understand and protect our oceans. So there are events like this going on all across the world, and hopefully will entertain and educate people into promoting our oceans. As I said, we came over on the ferry. The news today had some articles about World Ocean Day, and there's no more important time than right at the present day. Climate emergency and all sorts of things that we need to understand and protect our oceans more importantly than ever. Now, there's no better way to reinforce this message than, of course, there might be something going on in Glasgow in the autumn. This is COP26. This is the UN Climate Change Conference. And for those of you with an ear to the kind of the policy side of things, are well aware of the meetings going on. We've got the G7 going on in Newquay at the moment today, just started today. So there's a lot of interest and a lot of activity going on. John Kerry, US Secretary of State, has described COP26 as being the last best chance in order to try and help to protect our oceans. So we really are setting the scene for a really important year, and hopefully the UK, we can build on this and build on some of the foundations that have been laid through the past decades and work that have been done by SAMS and our friends all around the world in understanding our oceans. Okay, so rather pompously, I've probably entitled this Adventures in Marine Geology, Getting into Deep Water. It does feel like I started out getting into deep water, and at times we have. And I hope that this short talk will help reinforce that message that geoscience is as relevant as ever, and is important, of course, because it's working with friends, it's working with networks of people all around the world. As Todd has already said, we have our undergraduate program at SAMS UHI, the Marine Science program, and master's programs as well. Sending students, hopefully, once COVID is out the way, and I'm sure it will be, I'm an optimist, sending students all around the world. I've had some very interesting times, and I hope to be able to tell you about this, working in places such as Papua New Guinea, working on industrial aspects of our oceans, working around the Antarctic and around the Arctic, in the Chilean Patagonia with students such as Karen, working in the Arctic with Ricardo and guys like Christian and lots of other friends as well. Now, how relevant really is geosciences to our oceans? Extremely. For those with a keen eye on the BBC Science pages, you might see a great news story today. I'm here nervously hoping the Wi-Fi will hold up as I give this talk over the internet. There's a lovely story about the work that the University of Durham and NOC are doing at the moment, looking at the breaking of internet cables off west coast of Africa by submarine avalanches, by turbidity currents. There's a great way that geoscience is helping us to understand and improve the way that we use the oceans. This critical infrastructure these days, after lockdown and COVID, is to get secure internet connection. So there's a really interesting story. And of course, there are all sorts of other ways we could talk about this. So let's plow on and let's see how this goes, describing some interesting adventures in marine science. Now, this is Jessica. This is my daughter, Jessica. She's getting ready for her evening bath. We tended to do a low temperature wash because she didn't shrink as much. So she's peering into the washing machine, wondering what's going on. So we're peering into the oceans, and in a sense, I think this nicely encapsulates the sort of the issues and the challenges of mapping our seas. So really, geology, as I say to the students, it's obvious. Geology doesn't end at the shoreline. Of course, the rocks extend offshore. An interesting example is the interpretation of the continent of Zealandia. So you can see in that lower right-hand color map, outlined in pink, this is an area of rocks of shallow water, possibly continental rocks, that are shallower than the surrounding deeper ocean basin. So this is a continental fragment, a remnant that New Zealand, poking above the water, is part of. So this was 1995. So we realized perhaps we could interpret some of the seabed as being evidence for more continents. So we're still making these fundamental discoveries, and these fundamental discoveries are still to be found in the seabed. So there's an example from Mortimer et al. From the Geological Society of America, 2017. So peering into the oceans, like Jessica peering into the washing machine, can be a tricky business. So for this talk, I'd like to start off. I'm going to talk about some early days, hopefully give you some interesting early examples of mapping. I'd like to talk about the unfortunate big bang of seabed mapping, if you like. Show you some boat data, some vessel-based data, and then onto, as Todd and Axel have said, onto some examples from robots. So we'll see how we get on. So let's peer into the oceans. Now, incredibly, the original seabed maps, of course, used weighted lines. So there's a lovely map at the bottom hand of the screen, bottom part of the screen. This is the Southern Ocean, that's the Scotia Sea, and this is where I spent an inordinate amount of time measuring ocean depth using an echo sounder and watching that pen trace that fascinating line across the seabed and mapping out these these fracture zones. And you can see that curved trench there around the South Sandwich Trench, and these other little fragments like South Georgia there, between South America and the Antarctic Peninsula. A fascinating place and a fascinating area, and a privilege to do marine geology in this area. But of course, it started out even way further back than me pottering about in the mid-1990s in the Southern Ocean, sitting with a cup of cocoa, watching that pen trace a mark on a piece of paper and calculating the shape of the seabed. So what kinds of things would this kind of approach have produced? Okay, this is fairly ghastly, but I thought this was quite a nice example to use. This is an old paper from Marine Geology, And this is where we compiled those echo sounder traces. And in particular, in this example, we're tracing the echo sounder return from the seabed in order to determine the depositional processes, how the sediments or how that piece of oceanic crust got there. Was it erupted, or was it buried by something like Pete Tallin and the gang at Durham are looking at underwater avalanches? So rather crudely, I divided the seabed up into non-depositional, exposed basalt or eroded by currents, or depositional, mounded or buried by underwater avalanches, and came up with this this rather primitive map. But it's a good start. Now, the message I wanted to sort of pass over is these kinds of maps, any map really, is only as good as the position of the vessel that took that data. So those spidery lines on the top left-hand panel represent the position and the travel of those vessels of where we took the echo sounder data. So straight away you can see there are some big gaps, and that's an important point. We need to be able to cover the ground. We need to be able to exactly see the seabed in order to accurately make these observations and produce these maps. So early attempts for me, but in terms of seabed mapping, that kind of approach is quite useful in order to determine where we might be able to go next. Now, here's some pictures of sort of places around Antarctica. There's Erebus, the volcano in the Ross Sea. There's an ice camp from the Kate Roberts drilling project in 1997, and that's the South African icebreaker, the Agulhas. Now, these are all projects that I've been involved with over the past few years. They all relied on accurate positional information and accurate information on the seabed. In the case of something like that ice camp, we were interested in looking at the transition of Antarctica from a greenhouse world, if you like, a vegetated temperate Antarctica, to the current sort of icehouse conditions, the current cold conditions around Antarctica. Now, of course, Antarctica became oceanographically isolated, possibly around about 34 million years ago, with the separation of the continent from South America. So it was tectonics, it was the movement of the sea floor that enabled the southern continent to become isolated, and therefore ice sheets to grow with the addition of precipitation, possibly through North Atlantic deep water. So we were interested in looking at tectonic and climatic records. Finally, that little panel on the lower right-hand side was a lovely project that we did over a couple of years. And this was with Bhavani Narayanswamy at SAMS and friends at the University of Hamburg, and Avi in Germany. That's the German icebreaker Polarstern. And again, we needed to get samples of animals. It was the first survey of the biodiversity of the deep Southern Ocean. And so again, we needed accurate maps to be able to sample the right locations in order to determine what animals are living down there. So maps are key. So we can look at the echo sounder return, we can look at the depositional processes, we can also take slices down through the seabed using sound. So rather than look at an acoustic picture, sound can also be used to image sediments in a slice, and we can interpret these sediments as being the result of various depositional processes, such as avalanches or slow settling, or in the case of these profiles, by a long slope accumulation of sediments by persistent or semi-persistent ocean currents, thermohaline currents driven by density. These examples, beautiful examples from the Northern Rockall Trough. This was my old PhD area, and worked with friends at the University of Southampton, and above all, the British Geological Survey, led by Martin Stoker and Doric Stowe. These beautiful profiles, you can see lovely fine waveforms. This is hundreds of meters of sediment accumulation over up to millions of years. That bottom panel shows a transparent reflector overlain by very, very highly reflective sediments. And we can interpret that in a very simplistic way. We could describe those transparent sediments that are perhaps just a couple of meters thick in a wave form that are deposited from currents, overlaying these vigorously deposited current-controlled sediments underneath. So there's a simple climate signal, strong currents underneath and weak currents above. So there's a lovely way that we'd be able to map the seabed and very simply, interpret the seabed in terms of climate. Now, as a geologist, what am I interested in terms of climate change? Well, the big one is obviously, and the simpler one to go for is glacial interglacial cycles. Let's focus though on trying to get some good seabed maps. That's the key for this afternoon, is looking at seabed mapping and different ways of seabed mapping. Now, early surveys were conducted with a weighted lead line. This is a fantastically accurate but incredibly time-consuming way to map the sea floor. You literally lower a weighted line and you measure the amount of rope or wire that's been let out. You can see there a nice map with a series of weighted lead line surveys across a loch on the lower right-hand panel. Since the turn of the 20th century, the development of echo sounder and sonar, single beam echo sounder, enables a much more efficient way. But we're going to focus for the remainder of this talk on multibeam, full coverage. We're not just sending one ping of sound, we could send up to 25,000 pings of sound a second. So this is a highly efficient, automated way to resolve the seafloor in 3 dimensions. So in our geologist's arsenal, if you like, in our toolbox, we have our sonar. Is by far and away one of the most useful tools. Sonar meaning sound navigation and ranging. So we could image the seafloor by sub-bottom profiling, which I've just shown you some examples of looking down through the sediments. We can use side-scan sonar to image the seafloor in terms of its acoustic footprint, its intensity or amplitude of sound. We can use bathymetric sonar providing 3D images, and then we can go back, as I've already said, and hopefully sample, drill, or perhaps dredge these sediments. Now, all these approaches are dependent on the speed of sound in water. Now, the speed of sound is dependent on the density of seawater. So the density of seawater can be a bit hit and miss. So it's important that we do take essential measurements, take measurements of the speed of sound, of salinity and temperature through the water column, because otherwise you can get all sorts of interesting artifacts. So it's not so simple as just switching on your sonar and sitting back, as I did with my cup of cocoa, and watching that pen trace the sound across the sea floor, especially in deep water. Okay, so we'll focus on multibeam bathymetry. Now, very sadly, of course, in 2014, essentially we saw a change in mindset of how we viewed mapping the oceans. It changed from something perhaps esoteric or the preserve of the military, and became something essential that we really needed to do. And the event was the loss of Malaysian Airlines MH370, which went missing in March 2014. So this unfortunate event that has been highlighted in the wonderful review paper of Wolf 2019 has really made everyone sit up and realize that we simply don't know enough about the shape of our oceans, enough, if anything, about the shape of our ocean basins. This is a figure taken from the Wolf paper and shows the difference in the same area. This is off Western Australia, the search area for MH370. The difference between altimetry-derived bathymetry, this is satellite remote sensing data using sea surface height, and multibeam bathymetry. Great, the multibeam bathymetry, we're able to resolve those features into individual little mounds and rock plateaus. Look at the scale, that scale that I've highlighted in yellow, 20 kilometers. This is enormous areas of sea floor. So there's a huge challenge in looking for this aircraft. I'll just put this up quickly, and I just wanted to draw your attention to the pink boxes and the red box. So the pink area is that priority search area. This is 2014, 2015, I think it is, search, 60,000 square kilometers. The light pink there, 120,000 square kilometers. If we're to survey the entire of that sort of wide area search, it's an incredible 1.1 million square kilometers. These are phenomenally huge areas of seafloor to search. And of course, if you're looking for an aircraft in water depths of 5,000 meters, you really need very high resolution maps to be able to locate this. So this is an enormous challenge. But hopefully there is hope. The Nippon Foundation and the JEBCO 2030 Seabed Mapping project does provide us with hope. This is an idea by 2030 to be able to map most of our ocean floor. Here we are in 2021. By 2020, I think it was, last year, they had mapped 19% of the ocean floor. Still a way to go, but you know, we are getting there. It needs an enormous international concerted effort. It's a cliche, but I thought I would throw it in. Mars has been 90% mapped. You can go onto Google Mars and look at the Martian surface. You could argue Mars is a pretty tough place to go and map. The oceans are extremely tough place to go and map. Look at that scale again. This is the Noctis labyrinthus area of fractured basaltic rock near the Tharsis Mons volcano, and you can see the scale there, 250 kilometers. These are again enormous features. We know more about the shape of Mars than we do about our ocean floor. Okay, but there is hope. Here we go. Let's go closer to home. This is the UK Hydrographic Office last report, sorry. So this is September 2020. And this reveals the survey extent and the type of surveys around the UK. So the red, the deeper water areas, our lead line survey, about 63%. The orange, single beam echo sounder. If we take the light green areas and the dark green areas, we have approximately 33% or so of the UK currently mapped. It's a surprisingly small number. And there certainly needs to be a concerted push to try and understand our continental area, let alone all the oceans. But it's an interesting fact that only 10% of coastal states have their shallow water surveyed to a modern standard. What do we mean by a modern standard? Well, we mean the International Hydrographic Organization, or IHO specification, which is a tough specification, admittedly, requiring very precision instruments and good tidal measurements and velocity measurements. So it's interesting to note as well, 80% of the UK is under the sea. That's interesting. 70% of the Earth is ocean. We knew that, World Oceans Day, but as I've said, less than 20% is currently surveyed. Okay, let's draw in now, and I'm going to show you some examples. I hope I've set the scene for the need and the usefulness of seabed mapping. Here's a maritime chart. I love these things. Absolutely love maritime charts. I can sit and stare at them all day. This is a lovely area of the Sea of Hebrides. This is around the south of the Isles of Muck, Egg, and Rum. This is north of the Ardnamurchan Peninsula. Now, as a geologist, Ardnamurchan, fantastic. It's a collapsed volcano, possibly around 53 million years ago. This volcano drained of magma and collapsed, and has done all sorts of interesting things to the seabed. Now, that's a useful nautical chart, useful for navigation. What about the data that underpins that? What did they use to produce this beautiful chart? There's the multibeam data. This is how beautiful some of this multibeam data is. I'm geologically interested, and I'm indebted to good friends Dayton Dove, Tom Bradwell, and Joanna Gafira of the University of Stirling and the British Geological Survey. BGS are at the forefront of compiling and mapping this kind of geological data, and it really is beautiful. So we produced a little paper from this in I think it was 2012. Now, interesting on this, there's lots of things we could spend ages talking about. This is this huge fault. I don't know if you're able to see this wrench fault going out in a northwesterly, southeasterly direction, coming out from Ardnamurchan. Beautiful geological feature. It's not actually reflected that clearly on the nautical chart. Obviously, it's not really a nautical or navigational hazard, but for a geologist, multibeam data is absolutely terrific. I'm sure you'll agree. And friends with BGS, we went out in 2011 and drilled some of these places from the James Cook vessel, and found that a lot of these little wriggly red lines in shallow water, presumably 50 to 30 meters water depth, are lava flows, ancient lava flows from that Ardnamurchan volcano. Absolutely terrific stuff. Okay, so I'm going to show you all sorts of, hopefully, some interesting data. We're going to move just slightly south now. We're just south of Mull, between Mull and Oban. And for me, this was a tremendous project led by the Maritime and Coast Guard Agency and the Northern Lighthouse Board, the Geological Survey of Ireland, and other friends as well, across Ireland, Northern Ireland and Scotland. So we mapped 553 kilometre squared area, and we found all sorts of interesting things: pock marks, gas escape, I'll show you in a moment. We surveyed the Corryvreckan whirlpool, we'll come to that. And you can see this beautiful data. To interpret the multibeam, let's just get our heads around how this stuff works. The hot colours, the reds and the yellows, tend to be shallower water, meaning probably less than 50 meters water depth. And the green and the blue are deep water, perhaps 100 meters, maybe 200 meters or more. Interesting, on this slide, in the center of the image, you can see this diamond shape. What an interesting shape. This is just off Oban, and these are faults. These are big seabed faults that have pulled apart many, many hundreds of millions of years ago. And of course, this area is part of the Great Glen fault zone that runs through Mull and comes out around about Loch Buie there. So some interesting things. Let's zoom in on this data and just give you an example of how some of these geological features influence the sea floor. Now, what are we going to be looking at? Let's look at the main geological periods. Here we go from the Precambrian, so this is older rocks, about 570 million years, all the way through to amazingly younger rocks in the Tertiary, and then the glacial, the last 2 million years on top. Those red lines represent periods of sustained erosion where there's geological time that's missing, and therefore the sediments aren't present. Now, this map is part of the 1 to 250,000 series, the Argyll solid geology sheet by BGS. Guys, I urge you, if you do have a bored moment, go onto the Geo Index and have a look. This is all online. It's fascinating. All this geological information is available through BGS. But it's interesting to reflect on those surveys and to have a look at this geological map. If we take a closer look at the multibeam, here we can see how the older folded sediments, these are the Precambrian sediments, are softer. Surprisingly, the older sediments are softer, and the more resistant younger sediments, those 400, 350 million year sediments overlain by that very younger volcanic sediments, are the resistant blocks. And that really, it's kind of, in summary, sums up the sort of the main Firth of Lorn. We have softer folded rocks eroded into the deep areas, and then these more resistant platforms. And I'm indebted to Roger Anderton for Roger coming up with this beautiful cross section illustrating how these geological structures play a part in shaping our seabed just off Oban. Very quickly, just a few quick examples here. In particular, we can see that deep water, softer area that's been scooped out, presumably by glaciation and by erosion over many millions of years. And we can see these moraines left by ice sheets. Going back further in time, we can see these arrowhead folds plunging into the seabed. There's our softer units. And of course, that lovely pink area, there are resistant rocks. Now, there's a couple of things just to quickly highlight here. Look at the holes, the pock marks. These are modern, or relatively modern, a few thousand years perhaps, gas escape structures. This is possibly methane, and this is an area that Alan Audsley and Tom Bradwell at the University of Stirling are looking into, these pockmark structures. They're very common in this kind of fine-grained sediments, organically loaded from the sea locks. And finally, the little yellow box. Look at this. How beautiful is that? That's a submarine slide. as this is where the sediments have failed. I mentioned at the beginning of this talk how the sediments have failed off the coast of Africa, and the guys at the University of Durham have been looking into this. And you can see here how these sediments have collapsed fairly recently, difficult to say when, and have poured sediments down the slope. Now this is an issue, possibly not a major issue in terms of tsunami risk around Scotland, but is of course a major issue in some areas, particularly in volcanically active areas in the tropics. And this slide was included in a recent paper by Gareth Carter in 2020, I think it was. Okay, here's an example in the southern Firth of Lorn, just to the west of Easdale Island. Again, you can see the little, just to navigate our way around, the little black and white map with the red box illustrating the position of where we're looking at. So here we can see these rock platforms, which are principally sediments, the old red sandstone and the lavas, these exposed rock surface, some beautiful arrowhead plunging folds, and some of these lovely exposed Easdale slates. It's a lovely fabric there. Now we found something interesting in this area. There is a legend of two giants. There's Finn McCool and Benandonna. There were two fighting Celtic giants, and Benandonna was the Scottish giant, and he ran over to Ireland. He was throwing stones at Finn McCool, and they were throwing stones at each other. They were pretty upset, pretty fighting all the time. And Benandonna ran over to Finn McCool to Ireland, and he peeped into his bed. Finn McCool actually hid himself as a baby, and he frightened Benandonna so much that he ran back to Scotland. And lo and behold, it's only through seabed mapping that we're able to find evidence for this story. And there you can clearly see the giant's footprint, showing Benandonna did indeed run away from Finn McCool and ran back to Scotland. So that's nice. There are other mysteries and myths on the seafloor. There's the Corrie Vrecken. The Corrie Vrecken is an area of extreme tidal flow located between the islands of Scarborough and Jura. In this area, current velocities of up to 5 meters per second can be encountered. It's known as the Speckled Cauldron or the Old Hag. There are other whirlpools around the world. There's the Lofoten Islands, the Maelstrom, the Naruto Narrows in Japan, and the Old Sow in Canada. So this is a spectacular place and is a really interesting place to try and understand the interaction of the sea floor and those extreme tidal flows. And I'm very grateful to Christian Armstrong. Christian is a super PhD student. He is a super PhD student for the following slides. Christian published this this year, I think it was, or last year, forgive me, 2020. Here we can see some bathymetry of the Corrie Vrecken, the deep water areas there, about 200 meters deep, and the shallow water areas with the rock walls extending from Scarborough in the north to Jura in the south. Now, there's some interesting features, as well as being a wonderful piece of ancient geology. This is the Jura quartzites and the Scarborough conglomerates, so about 700 million years old. In the areas west and east of the Corrie Vrecken, we can see the effect of strong tidal flows on the sea floor. If we focus on the western extent, first of all, you can see this spectacular dune crest. I'm looking at A and B in the top left-hand corner there. These are 4 dune crests, 200 to 400 meters long, 190 meters wide. So the complete ridge there is 6 kilometers long. And it provides an area extent of sand that's been swept out of the Corrie Vrecken and reworked of about 4.3 million cubic meters of sand. An astonishing area. Just to the south, we see what we've termed the Great Race Dune Field. These have these series of marching dunes. These are mobile bed forms, 7 meters high. They're 4 to 130 meters in wavelength, measured from crest to crest. And interestingly, the wavelength decreases away from the channel, so they become more and more frequent and closer together away from the channel. So the model that we have for this is the result of the flood flow and the flood producing the Great Race. And what we see is the vortices being extended, these circular flows extending out from the Corrie of Wrekin. And I'm very much, Christian and I are indebted to Andrew Dale of SAMS, who's worked on this before we got any of this bathymetry data. Andy's been working on these kinds of ideas, looking at extreme tidal environments. So these vortices are producing these dunes to the north, and the Great Race is producing our Great Race dune field underneath. Now let's have a look at the eastern extent of the Corrie of Wrekin. This area, I have to say, is just weird. Look at these features. Look at the scale here. Water depths of about 30 meters, the lovely pink color, down to about 100 meters or so with the green color. So here we see multi-crested dunes, 15 meters high, a kilometer square of sand, reworked sand, with these lovely superimposed bed forms. I think you'll agree that southern dune is like a braided rope, really fantastic, and illustrates, if we take the analogy that these sediments are responding to the turbulent flows that are generated within the Corrie of Wrekin, the sediments are a signature of the turbulence that's being generated at the sea floor. And again, the model here is of our ebb flow and the interaction of three currents in the southern sound of Ling around Cruve Haven and just to the east of the Corrie of Wrekin. So examples of extreme tidal flows. Another area that's very interesting is the Falls of Laura. Many of you will be aware of the Falls of Laura, which is a 30-kilometer Loch Etive, is the exit of Loch Etive, a 30-kilometer sea loch just to the north of Oban. This sea loch is very interesting in that there's an entrance sill, a shallow sill, 7 meters below mean high water. So again, it's the bathymetry, it's the shape of the sea floor that produces the very strong tidal flows of about perhaps 3 meters per second under the bridge. Also, we have a difference in tidal height. We have an internal tidal range within the loch. Those of you familiar with the tides are relatively small, about 1.8 meters at spring tide. Inside the loch, outside the loch, of course, at springs, it's about 4 meters. So there's a huge amount of water that's trying to get into the loch and a huge amount of water trying to get out of the loch at different states of the tide producing the falls. Now, if we look at the seabed, we've managed to survey this area. It's adjacent to SAMS here in Oban. And we can survey the seabed here, and this is what it looks like if we drain the water and have a look through multibeam sonar. And I'm indebted to friends at Norbit Multibeam for these data. And here we can see again hot colors down to about a couple of meters water depth, and the cold colors down to about 45 meters water depth. So there's our rock sill, and we're going to focus just east of the bridge in an area of dunes. These are submarine dunes, and again, Christian is looking at this data, and the idea will be, how much change do we see on the seabed? So in this area, we're lucky enough to have repeat surveys from 2014, 2020, and we'll go again in 2021 this summer. And what we want to do is, Christian's been mapping the seafloor, and we're going to do repeat surveys. Why are we interested in just repeatedly mapping the seafloor? Well, in areas of extreme tidal flow, the seafloor can change quite dramatically. In this case, Christian's marked out the gravel waves. We have these beautiful areas of reworked sediments and ripples. How much does this change? Now, this project is in partnership with Scottish and Southern Electricity Networks, with the gang up in Inverness, and we're indebted to these guys for their help. Because, of course, if you're laying an electricity cable for the push for renewables in order to build a robust grid bringing electricity from, say, offshore or wind farms, then you need to understand how much mobility and how much change, how much dynamism there is in the seabed. So that's what we're trying to understand. Now, the model that we kind of have a working model here is how the bathymetry is influencing the flows. Here we have ebb flow in white, the flood in grey, but the sediment transport really is the interesting thing on that top panel. And this shows the net sediment movement generating our large dunes, submarine dunes, and the mobility of the sediments. Even though it's gravel, mostly gravels and cobbles, under these extreme flows, this material is able to move around. So it's the shape of the sea floor that's producing these very strong tidal conditions. Okay, I'm just going to pause for a moment here. Here's a lovely, pretty slide. We're going to change tack now. So I've been talking a little bit about the vessel-based observations that we can look at the sea floor from multibeam sonar and look at the sea floor in 3D. Now, I introduced this talk talking about the climate emergency and John Kerry and the World Oceans Day that we're celebrating at the moment, and our ambitions towards protecting and sustaining our oceans under the present climate emergency. Now, the Arctic is an area that's seeing some of the most rapid warming on the surface of the Earth. So what we want to do is, can we demonstrate how the signature of the seafloor, glaciers on the seafloor, marine terminating glaciers, have left their mark? And can we interpret those submarine landforms, if you like, the shape of the seafloor, as being a response to warming, perhaps, or to the behavior of the glacier? Now, to reinforce this point, I'm indebted to Finlo Cottier. Finlo is Professor of Polar Oceanography at SAMS. And this is a lovely bit of data that Finlo has compiled from 2002 to 2018. This shows the sort of seasonal warming and cooling, winter, summer cooling. If you look at the trend over those last sort of 16 years, if you fit a trend bar, you can see we're seeing a gradual warming, with Atlantic water making increasing incursions into Western Svalbard. And we're going to focus on interpreting perhaps the influence of that Atlantic water into the fjords of Western Svalbard. And to do that, we need to change tack. We need some new instruments. Glaciers that are retreating or advancing collapse. These are hazardous environments. We can't really go in with our vessel and survey underneath a glacier front. You can do, but it would be pretty stupid because it would probably fall on you. So we need something else. We need a better way to efficiently and safely map these hazardous areas. One of the new approaches, I suppose it's not that new, over the past 10 years perhaps, we've seen an increase in the technology of autonomous underwater vehicles. The use of robotics, of untethered instruments, so an ROV, a remotely operated vehicle, is tethered, and that's what we're using here in Strangford, is also useful, but untethered instruments that think and map for themselves is really, really fascinating, and is a game changer, I suppose, and might help us in the search for aircraft such as MH370 in that unfortunate event. This is a picture of the autonomous underwater vehicle Freya. We operate her on behalf of the National Oceanography Centre. She's a terrific instrument. She's downstairs, actually, at the bottom of the stairs. She's about to go on to charge for tomorrow morning's survey. So using this instrument, we give her a pre-programmed mission, we send her off, and she'll map the seabed. She'll come back, hopefully, and we'll download the data and start to interpret. So these are a really useful instrument. Now, in 2016 and 2017, we were delighted to work with the Norwegian Polar Institute and the University of Svalbard on a project to try and look at very high resolution mapping using an autonomous vehicle in front of these glaciers. So we chose the glaciers of Fortenda Julibreen here in Kongsfjord in Western Svalbard, Komwebreen, Kongsbreen, and Kronebreen. So I'll show you some of these data and see what you think. Now, to try and understand what we were doing, really the project was to have a future look. We were going to look at the current status of those glaciers and the imprint they've left on the seabed, but also to look to the future and map a fjord that is currently not glaciated, and that's Dixon Fjord. So we set up a camp there on the tundra in a kind of a river setting on a tidal mudflat and surveyed this area. So we looked at two end members, a sort of status quo, if you like, looking at the marine terminating glaciers, and a non-glaciated fjord. I'm going to focus on the data from those glaciers just for this brief moment. Now, here's some models of the shape of the seabed that might be the result of different behavior of glaciers. And this is from Dowdeswell's et al., Dowdeswell's Atlas, 2016 Atlas of submarine glacial landforms. So here we see different scenarios, top left, a mild setting, and right at the bottom right, a high polar setting with basal water drainage, meltwater drainage through a deforming till. Till is the soft sediment that's been deposited directly from an ice sheet or from a glacier. So we can use these models to try and help us interpret the response of the glacier. First of all, here's two beautiful little surveys from Fortenda Gili and from Conway Bream, and I'm indebted to our two marine science students, Hannah and Valentina, for helping us to interpret and accurately map this data. Now, these two areas are dominated by these ridges, beautiful little feathery ridges, and these are moraines, probably little seasonal push moraines. Both these glaciers have now retreated back onto land, so we can see the effect of the glacier's retreat by tracing back those moraines. So that's the result of a kind of a slow, steady retreating glacier. Here we have two beautiful glaciers that are responding in a different way. These are rapidly retreating, perhaps 300 meters per year. This is Kongsbreen and Kronebreen, and I'm indebted to Hannah again and to Hector, who's done a great job in mapping these areas. Now, the difference being, both these glaciers are rapidly retreating and they're responding to ocean warming. And they also have the lubricating effect of meltwater discharge. So we have rapid retreat meltwater, and you'll notice that these surveys lack those beautiful little feathery moraines. So very, very interesting. In addition to observations of the sea floor, we can also observe the effect of these meltwater discharge using the autonomous vehicle. These are meltwater signals here from Kronebreen put together by James Coogan. James is looking at AUV data from glaciers at the moment, and James has done a great job in putting together some of these quite complicated data. Here we can see salinity and temperature, and on the top panel you can see a fresh and cold signal there, which could well be that meltwater discharge from the glacier. So we have a very compelling case to be made for rapid retreat, ocean warming, and active melting of the glaciers. If we put all this together with USGS Landsat imagery, we can trace back the retreat of those glaciers, in the case of Fortenda Gili since 1976, the extent of our survey that covers seabed of that age. And in the Kronebreen and Kongsbreen areas, you can see for yourself very rapid retreat. Those oldest areas there, 2011, well, actually 2014, looking at that. So the Svalbard glaciers are very much in retreat, responding to ocean warming. Okay, we're coming to a close, but I'd just like to take a quick look, a forward look. What's next? So the use of autonomous vehicles in polar environments is proving its worth. This has been done before by a number of people, and it's really interesting to try and interpret the seabed as a response of the glaciers, perhaps to climate or to other mechanisms. Now, our next project, I'm delighted to say, is going to Greenland, looking at the really big glaciers on Greenland. So this is a 3.5-year project with friends from the British Antarctic Survey, from Durham and Leeds, and from SAMS UHI, including a cruise to go into the Kangerlussuaq fjord on the new polar research ship Sir David Attenborough. So this is going to be a great project that's just about to start. Why Kangerlussuaq? Why Greenland? Well, the marine terminating glaciers of Greenland drain the ice sheet to the ocean. From 2000 to 2012, this discharge increased by 18%. 30% of discharge is only from 5 glaciers, including Kangerlussuaq Fjord, Helheim, and Jakobshavn. So it's leading to rapid ice loss, which has obvious implications for sea level ecosystem change and changing perhaps ocean circulation. Now, Kangerlussuaq in southeast Greenland contributes 5% of the mass loss from the Greenland ice sheet. And there's very good evidence of observations that it's thinned and accelerated its retreat from 6 kilometers since 2005. Since 2015, it's retreated another 5 kilometers back to its current precarious position next to an overdeepened basin. So it's a really good target to try and understand a really large glacial system. We're going to use all sorts of interesting technology, including our autonomous underwater vehicle, as well as the Sir David Attenborough Polar Research Ship. And you can see moorings, autonomous vehicles to study the meltwater plumes, the oceanography of the fjord, the links of oceanography to the behavior of the glacier and the loss of mass from the Greenland ice sheet, as well as sediment coring, to look at records of past environmental change around Greenland. So that's what we're going to be doing in the future. Okay, so I'll close to finishing off. Let's just pause for a moment and think about the future. What do we need to do? We need to, obviously, here on World Oceans Day, to map and understand our planet's oceans. We need to better use these technologies, such as robotics and remotely operated autonomous vehicles. We need to make bathymetric data freely available. It's quite difficult sometimes to get hold of this really nice data. And we need to continue to develop new technologies, such as swarm technology, using multiple autonomous vehicles or robotic vehicles, perhaps in novel and interesting ways to deploy them that communicate with one another or pick up data and transmit data more efficiently. So it's an exciting time ahead. There's all sorts of challenges. There's all sorts of interesting things we can do. But of course, here on World Oceans Day, let's pause and celebrate our wonderful oceans and celebrate together, and also celebrate for those who also haven't been able to join us here today. Thank you very much, folks. And I'll stop sharing here.
Thank you very much, John. Your enthusiasm for marine geology never fails to amaze me, so that's wonderful. We have a few questions, largely focused around the sort of attempt to globally map the ocean. But to begin with, we have a very specific question, which I'm going to read out to you. So you mentioned the Congo submarine canyon at the top of the lecture. And it looks like it's a surface feature created by a meandering river, but seems to extend a very long way to significant depth. How did this feature form? Has it always been a submarine feature, or was it formed on land and subsequently submerged?
Okay, that's a fantastic question. Whoever gave that in, that's a really good question. Yes, the answer's yes. That's not a very good answer, is it? So canyons form, I think what you're looking at on the BBC website is a meandering channel on the sea floor. Fascinating structure. Now that is formed in soft sediment by density currents. If, like me, you've ever waited for a bus on a rainy day and stood next to a muddy puddle, what you must always do is jump up and down in that puddle, and you will generate muddy turbulence that runs down into the puddle. You'll see clouds of mud. That's what's generating that meandering channel. So the coarser sediments within that density flow is effectively eroding the meanders, just like a river on land. But that is definitely a submarine feature. Now, if we trace that back into shallower waters, then we see an interesting phenomenon, because the channel will then transform itself into a much more V-shaped canyon, typically. Now, that V-shaped canyon could well be the result of exposure during lower sea levels, for instance, during the last glacial maximum, perhaps about 25,000 years ago, where sea levels were 120 meters lower than the present day. So that is a that is an exposed river feature, but of course, in the deep water, that's quite definitely the result of deep ocean density downslope currents. Great question. Love turbidites, love turbidites.
Thanks very much, John. The next question is from one of your colleagues in the Professoriate. Svalbard and Greenland have great areas of exposed rock, but do you have examples of following features like the Ardnamurchan ring dikes offshore? And does this tell you that anything new about onshore solid geology?
Oh, that's a tricky question. Yes, Greenland has wonderful, very old sediments. There was an interesting news story, and I'm speculating here. Of course, there's been an impact crater that's been very recently exposed in northwestern Greenland. Now, there's an interesting point about that, is that impact crater could relate to what is referred to as the Younger Dryas climatic cooling, and that's an impact probably around about 12,000 years ago. So that's impacted, that ring structure has developed in Greenland, but is a relatively recent event. The rocks in Greenland are up to 3.2 billion years old, and they preserve a record of Earth's history very, very early on. Just as the rocks and the ocean basins were forming. So there's a fantastic record of Earth's early history and a great example of a ring structure recently exposed that is a very exciting find if proved correct,
Thank you very much, John. I've been asked to draw the questions to a close because we're a little bit tight for time, unfortunately. So you get off very lightly, but I have a note of them. And we can pursue that when we get to meet, assuming we will get to meet again one day in the flesh. So now I have the tremendous honour of welcoming you to the Professoriate. So I've been asked to say a few words around that. Myself, I've been a member of UHI Professoriate since being awarded my personal chair in 2018. It was then, and it absolutely remains, a tremendous honour to have become the first SAMS UHI chair, and something I reflect on fondly quite often. Colleagues should know I first met John Howe 23 years ago. We were interviewed at SAMS UHI on the same day. We started work on the same day, and we shared offices for many years. Indeed, our lives have been inextricably linked ever since, because just short of 2 years ago, John even bought my old house. So consequently, it really gives me enormous pleasure to welcome him to the UHI Professoriate today. The term professor can mean quite a lot of things, and unfortunately for some it still retains connotations of the lofty academic in their ivory tower. But for students it presents a fount of knowledge and occasionally some genuine inspiration, and John certainly fits that bill. For fellow academics, it defines a goal to demonstrate a real mastery of a discipline that we're recognised for by characteristically judgmental peers, and so it is quite an honour to receive this title. The idea of a university as a place where professors both advance knowledge and teach students, importantly, goes back to the founding of the University of Berlin in 1809 by Prussian philosopher Wilhelm von Humboldt, and it's now called the Humboldt University of Berlin. And Professor Howe is the true embodiment of that great ideal. He does indeed carry an international reputation for his work in paleoceanography, but quite magically has a mastery of teaching that results year after year in nominations and awards from the Highlands and Islands Students Association. Sometimes for his inspirational teaching and also for his superlative supervision of dissertations. So today's award really is very fitting for the history of the university sector. He now joins the senior academic cadre of the university. It's a truly student-centered institution, and so John and his approach fit extremely well. In his new role, his journalistic skill as a communicator will make him a consummate ambassador for the university, working with communities, business and influencers for the benefit of the institution, but also the region that we serve. Just past our 10th anniversary, UHI already has a professoriate in the region of 50 strong, which is fantastic, specializing in subjects including nursing, pedagogy, archaeology, history, engineering, and much more. And now we can add marine geology to that list at long last. Ordinarily at this point, I should take Professor Howe's hand, shake it warmly and pass on a gift from the university, but in these COVID times, I shall just have to give him a little something at a later date. For now then, please join me in welcoming Professor John Alexander Howe to the Professoriate of the University of the Highlands and Islands, with a brief round of applause. And thank you everybody for your participation. If you're interested, there'll be further events from the university, and you can find out about those through the university's website. Our next events, Jill is just telling me, are Leading Health Research and Innovation on the 10th of June at 4 p.m. and Rural Health, Why Our Connections to Land, Landscape and Community Shape Our Well-Being. And that will be on the 17th. So please do check out the UHI website for details. And for now, I wish you a very good evening and thank you all for participating. I hope you enjoyed the lecture and we'll be able to buy John a small glass of something whenever you meet him in his travels around the university in the Highlands and Islands. Thank you. Goodbye.